hit record. And then I'll go over what you should have gotten yesterday. The scale factor for this one should have been 2. It's an enlargement. The scale factor here, because it says A is the original and B is the scale diagram. The scale factor here is 1/3. It's a reduction. These bottom two, the scale factor here is 1/2. It's a reduction. And the scale factor is an enlargement, and it should have been 3. Is there anyone who would like me to go over any of these questions? Yes, Zara. This one? Okay. So scale factor is a measurement in the scale diagram divided by the same measurement in the original, or the corresponding measurement in the original. And it says in the question that A is the original and B is the scale diagram. So the scale diagram, if I look at, it doesn't matter which side we look at, if I look at this guy here, this length is 2 in the diagram. This length is 1, 2, 3, 4, 5, 6 in the original. So it's going to be 2/6, so that's my scale factor. Is going to be the fraction 2/6. And then this is divisible. We always want to reduce our fractions as far as we can. Both of those are divisible by 2. 2 divided by 2 is 1. 6 divided by 2 is 3. So your scale factor is 1/3. And then the second page were these questions here. There was 3 of them. Find the scale factor. Oh, where's my work? The answers for these ones are 4 and enlargement, 1/6 and reduction, and then 300 and enlargement is what you guys should have gotten on this page here. Comments, questions, concerns, is there anything there anyone would like me to do? Comments, questions, concerns, going once, twice, thrice, sold. Okay. So, let's warm up. So we're not going to do all of these. We'll do 3 of them together and talk about them, and then we'll move on to what we're looking at today. If you recall, or for those of you who weren't here, finding a scale factor is just a multiplier that takes you from a real object to a diagram or model of that object. So when everything's pictures, it's kind of hard to do this, to conceive this. So we're going to look at some maps today a little bit. If I want to find the scale, so in this particular set of examples, they say that the original is either on the left or the top, depending on how the pictures are oriented. The scale diagram is on the right or the bottom. And if you recall, or we're not here, to find a scale factor, what you want to do is you want to take a length in, or a measurement in the scale diagram, which I've been calling the letter D, and you're going to divide that by the corresponding length on the original, which I've been using O to refer to it. So this is the original. This one is the scale diagram. So then to find the scale factor from these, we're just going to take a measurement on the diagram. It doesn't matter which one you choose. So we could choose 16 or we could choose 6. It doesn't matter. Let's choose 6. That side there. And the diagram is going to be, the diagram measurement is 6. My original length is the corresponding side. So for those of you who are away, the corresponding side is the same side, but in the smaller, or like in the other one. So this one is this angled piece here. So the corresponding side would be this angled piece here. And so that side there has a length of 3. So 6 divided by 3 is going to be 2. So this one would have a scale factor. That means that this diagram is twice as big as that diagram, or this diagram is twice as big as this original object. So that's the stuff that we were doing yesterday. So then if I'm going to find the scale factor of number 2 here, What's the scale factor going to be? We have to be careful what we choose to use. We can only use, if we're finding a scale factor, we can only use information that's in both triangles, or sorry, both shapes, whatever the shape happens to be. In this case, they're rectangles, not triangles. So what sides do we have to use in this one? Yeah, the top or bottom. They're both rectangles, so this is also going to be 25. So we'll take these two bottom ones. And so the scale factor then is going to be 25 over 10. It said we want the diagram, which was the one on the right, divided by the original, which is the one on the left. And so then this thing is going to reduce to what? What does 25 over 10 reduce to? Yeah, 25 and 10 are both divisible by 5. 25 over 5, or 25 divided by 5 is 5. 10 divided by 5 is 2. So then this is the scale factor that multiplies the smaller object to give you a larger object. Lastly, we'll take a look at number 3. What's the scale factor going to be for number 3? We'll just talk about this class. Someone other than Hassan joking. If you're on your phone, please put it away. Lunch is over. What are the two corresponding sides we should use for this question? Yeah, Matthias. Not Matthias. Okay. You can zoom in on 3, make it easier to see on the screen.
40 and 48.
Yeah, 40 and 48. Those are the same we have. That's the only set of sides that we have labeled in both. So we use that guy and that guy. The one on the right is the diagram, so it's going to go in the numerator. The original length is going to go in the denominator, and so then this thing can be reduced. 40 and 48 are both divisible by what? Both divisible by 8. So 48 divided by 8 is 6, and 40 divided by 8 is 5. So then this is the scale factor. 6/5. Or if you wanted to put that into a decimal, be 1 and 1/5, which is 1.2. So this is the stuff I had you guys doing yesterday. Are there any questions, comments, or concerns as we review this stuff? Why? Well, who got it? Okay. Flip the page. Here we go. So I referred to this, what we're going to do today, I referred to a little bit in the first lesson. We're going to take a look at it today in more detail. In lesson 1, we represented scale factors as fractions always. The scale factor was given the fraction, the length in the diagram, divided by the corresponding length in the original. But I did mention that this is just a ratio. Whatever this is, scale diagram divided by original, you can rewrite fractions when they're defined as ratios another way. You guys have all seen the colon notation for ratios, yes? We've seen the colon notation for writing a ratio? Some of you are nodding. This is good. So equivalently, what we can do, right, and often what you'll see, especially, I think I referenced with you guys, maybe it was in my other class, if you're building scale models of things, you'll see it drawn this way on the scale model. Instead of writing it as a fraction, you can write it as a ratio using this notation here, where the scale diagram numerator becomes the first listed object. Then you draw write a colon, and then you write the original, or then you give a value for the original measurement. You can write anything you can write as a fraction, you can always write as a ratio like this, where the numerator becomes the first thing listed, the denominator becomes the second thing listed. So this first little chunk that we're going to look at is just an exercise in converting back and forth with those. This is an example we looked at yesterday. We had a car, a scale diagram of a car and an original of the car. When we were looking at this yesterday, we said, okay, well, scale factor is the A length in the diagram divided by the equivalent length in the original. We did one like this. So the scale diagram length is 3. That became the numerator of our fraction. And the original length here was 15 centimeters for the corresponding measure. And then we took the fraction and we reduced it. We said, okay, well, the numerator and denominator both divisible by 3. 3 divided by 3 is 1. 15 divided by 3 is 5. So we said the scale factor is 1/5. But we could take this same thing and we can rewrite it with this colon notation. We would just say that this is 1 to 5 is how you read this. 1 to 5. And what that means is that for every 1 centimeter in your scale diagram, the actual object is 5 centimeters in real life. Or so if you're building scale models, if you're a model builder, does anyone build models? Do people still do this other than old people? Not really, okay. When you're building models, depending on the kind of object that you're building, they come in different scales. So some of them are, like for example, 1 to 72 is a common size of model airplane scale. Airplanes themselves, while large, are not ridiculously large. And so what this means is that in a model like this, 1 centimeter is 72, so 1 centimeter on the model is 72 centimeters on the actual airplane. So this is going to create a very small model for a large aircraft. But they also come in something like this, 1 to 48. So if 1 centimeter on a model is 48 centimeters now on the plane, this is going to create for you a much larger model. They also come in 1 to, I think it's 1 to 32. These are common sizes of models for aircraft builders, for those of you who are interested in such things. Cars come in different scales because a car is a smaller object than an aircraft. But if you wanted to build a model boat or a model tank, for example, boats are ridiculous. A model ship looks like this, 1 to 300. So 1 centimeter on your little model boat is 300 centimeters or 3 meters on a larger, on the actual boat. So these different kinds of scales, they represent the same kind of thing. The smaller the, well, I guess the larger the ratio, the smaller the fraction, the smaller the larger the real object's going to be, or the smaller your model is going to be, conversely. So this might be, if you're into model building or you are interested in getting into model building, this is how you'll often see these ratios. But for anyone who's ever used a mapping program like Google Maps, for example, you'll see scales on there as well. So let's go take a look at Google Maps, for example. They give their scale slightly differently. Where is my, I had it open earlier. Is it still open? No. Okay. Okay. So there's a map of the Fraser Valley. If you've never played with Google Maps before, shame on you. And often what you'll see in these, well, on Google Maps, it's always in the same spot. It's this object down here. This line and this measure are how computer maps will give you their scale. You can see as you zoom, the scale changes. You see that this length here is equivalent to 10 kilometers in the actual world. And the reason that they give it like this, they don't say that 10 kilometers is X amount of centimeters, is because, so they give this line here, depending on the size of monitor you're using, like the TV, for example, it's going to have a different scale than it would be if I just took the same map and slid it over my computer. if you're looking at it on the TV, what this scale is going to represent here is that whatever this measurement is, take a measure, that is 5, 6, 7, 8. The current scale for this rendering of the Fraser Valley is 8 centimeters on that picture as it sits on the TV screen is equivalent to 10 kilometers in the actual world. So now we can start to use this. We say, okay, well, I want something that's 8 centimeters long. Let's grab a piece of paper. Why not? This one here. I want a paper that's 8 centimeters long. Boom. Just drop the pizza everywhere. And now, if this is how I'm going to keep this thing zoomed, every chunk, there we go, every chunk on my map that is this big is going to represent 10 kilometers. So I could throw this here. I could say, okay, well, to get from Cultus Lake, which is that lake right there, I want to go a straight shot. That's going to be about 10 kilometers. Abbotsford to Mission, about 10 kilometers. Langley to Walnut Grove is about 3/4 of that. So, depending on what the rendering that you're using, this is going to change. And then depending on how this thing zooms, the scale is going to be different. You zoom out a ton, and now all of a sudden, now all of a sudden zoomed out like this, 7 centimeters is equivalent to 100. And again, they can't give, on a map like a digital map, can't give a scale like this because it's not going to be 8 centimeters on my computer. It'll be different. But back in the day, they used to have maps and books. Here's us. Right? Yes, that is the field. We are right here. This is my classroom. Actually, this is my classroom. This is Keely's classroom, right? No, Sue Center's below us. This is upstairs. Yes. So we are right here. This is us. Keely's class is right here, through this wall. These guys there. So in your notes, if you take a look, I actually put this picture is on there. I didn't photocopy super well. It's very dark. But you can tell that, hopefully you can tell, this is what is on your notes. So let's take a look at it. So maps use these scale diagrams the same way. In the picture that I've given you here, I'm telling you that the distance between the goalposts on the map is, it's actually not quite 10 centimeters. If you grab a ruler and measure it, it's 9.5. But for the sake of keeping the math simple, we'll round that, call it 10 centimeters. The goalpost is this guy here and this guy here. The uprights on either end of the field is 10 centimeters on the map, but the actual distance out on the field is 11,000 centimeters, or 110 meters. So for this zooming in on the field, what's the scale there? Well, the scale on my map, if you recall, Scale factor is the diagram divided by the original, or when I say diagram, a map is just a diagram of the way the world is. So a map is the diagram. So the scale factor there is going to be 10 over 11,000. That's reducible. Divide them both by 10. That's going to give me 1 over 1,100. So 1 centimeter on the map is 1,100 centimeters out on the field, or 1.1 meters. Sorry, 11 meters out on the field. So rewriting this thing, just in this new notation, would just be 1 to 1,100 is how you'd see it written. So all I want you to do, and I'm going to give you about 8 minutes to do it. 8 minutes? 9 minutes? There's 6, 7, 8, 9, 10, 11, 12 questions. I want you to find the scale factor and write it in that new notation. That's all I want you to do. On your mark, get set, giver. Take a look at these, and I'll help where necessary. Well, forget your scale factor is a length in the diagram divided by a length in the original. And if you read the instructions for all these, the original is on the left, the scale diagram is on the right. Take a look at all of those. So this should be 1 to 3. That's going to be 12 over 2, which is, yes, sir. You are, unfortunately, I'm not supposed to let you leave. Sorry. Should have done that at lunch. 11 over 1, which is 11 to 1. This one is 20 over 3, which is 20 to 3. This one is 40 over 10, which is 4, which is 4 to 1. This one is 18 over 3, which is 6 over 1, which is 6 to 1. This is 3 over 14, so this is a 1 to 14. This is 42 over 7, which is 6 over 1, which is 6 to 1. This is 14 over 154, which is 1 over 11, which is 1 to 11. This is 17 over 60,350, which is 550, so 1 to 3, 550. Okay, so I'm done. Hope you're done as well. Get them done. All I care is that you actually do things. That should be able to do. Because that's for 2 notations. So this is 1 over 3. Yeah, it's more pro. Take your switch. Who's this? You don't know who this is? It shouldn't be up. They should be able to take it. should be awake. So put it away. Yes, sir. Yes. It's not reducible. That's what I was thinking. No, you just reuse colon notation. So you take, yeah. So find the scale factor is always the length in the diagram. Divide by the length of the original. This one is off. It says, so the diagram on the right is, the picture on the right is the scale diagram. The original one, 5. Take one already found. Change notation. It's always something, yeah, we can rewrite it like this. It's always numerator to denominator. Yeah, so these ones. That was correct. It's whatever was in the so whatever was in the numerator is the way I wrote it. Okay. But it's written here. Scale diagram was the numerator, scale diagram. Original length was the denominator. Yes, sir. Sean, the IB department asked us for recommendations for students that we think would benefit from considering IB courses, and I wanted to let you know that I put your name on that list of students that I recommend. Well, no, you still have to convert it to the fraction notation. Sorry, the colon notation. So this one is 5/15. You reduce this to 1/3. And then down here, I want you just to rewrite it using the colon notation. So the numerator comes first, then the colon, then the denominator. Yeah? What do you mean? Oh, 1/11. It would be 11 to 1. Yeah. And this one would be 20 to 3. If it's not reducible, you leave it as is, yeah. Hassan Joe? Oh, and Samira. You don't have to do this, but all the teachers were emailed out and asked what students we thought should consider the IB program, and I put your name on there. Austin Joe, did you hear what I just said? Same thing. Akam. That's it. I'm just letting you know that I've done this. We emailed out for students that we would recommend to consider the IB program, and I put your name on it. Just let Okay, let's take a look. So, here we go. This is what you should have gotten for these guys here. Here's the first four. The first one, you're writing it as a fraction, you're reducing the fraction, and then your second answer takes it and it wants you to convert that into this new notation, this colon notation. All it is writing the fraction as a ratio. So 1 over 3 rather becomes 1 to 3. The numerator is the first one listed. Instead of the fraction, you've got the colon, and then the denominator comes second. So this one, if you've got a whole number, so 6, this is the same as 6 over 1. So this would be 6 to 1. 2 over 7 becomes 2 to 7. 1/5 becomes 1 to 5. Stop me if you'd like me to go over any of these. If the things are not reducible, obviously don't reduce them. So this one, 11 over 1 is just going to be 11 to 1. 20 over 3 becomes 20 to 3. Comments, questions, concerns on this front page? Is there anything there anyone wants me to do? Going once, twice, thrice, sold. The second page would look like this. 40 over 10 reduces to 4, so that would be 4 to 1. 6 to 1, 1 to 14, 6 to 1. You want to be careful. Always check to see if something is reducible. So in this case, both of these were divisible by 3. Both of these were divisible by 6. And then the last two look like this. 14 over 154. Both of those are, in fact, divisible by 14. So it becomes 1 over 11 or 1 to 11 in colon notation, ratio notation. And then 17 over 60,350. It's not obvious, but both of those are, in fact, divisible by 17. So it's going to become 1 over 3,550 or 1 to 3,550. Questions, comments, concerns about any of those? Is there anything anyone would like me to go over or discuss further? All I hear is the scraping of a Slurpee straw on the lid, so I'm going to keep going. Here we go. Flip the page. There is useful information that we can glean using scale factor. So I said before on the very first day, I said that if the scale factor is the same everywhere, what you have, or what we define that to mean is that these are mathematically similar objects. And then I said we'd come back to it in a couple days. Here we are. So similar figures in math are figures, shapes, objects, diagrams, etc. that have the same shape, but they are allowed to be different sizes. Either they can be an enlargement, they can be a reduction. But what needs to be true for these is that all parts must have the same scale factor. Good, we're still recording. I love that. So this is different than the requirement we would use in the English language. If I said that things were similar, we could talk about all sorts of things being similar in different regards. In some ways, you could say that Carson and Alex are sort of similar. They're both wearing hats. They're both wearing gray hoodies. They are obviously different people. The hats themselves are different, but they are dressed sort of similar. They're both wearing No, one's wearing shorts, one wearing pants, so that's where the similarity ends. So in English, that word similar has a lot more flexibility with what it actually means. In math, it's really rigid. Similar objects have to have those same scale factors. This whole row, except for Hassanjot, is similar. They're all wearing black on black on black. Hassanjot just decided to wear. Hassanjot, are you wearing a black shirt underneath that? Okay, take that jacket off. This whole row is similar. It's black on black, top and bottom, all the way down. I'm not talking about you. I'm talking about this row right here. Matab to Sean, all of them. Black on top, black on bottom. Well, except Acom. I take it back. Math, it's more rigid. Math, you have to have a scale factor that is similar all the way down. So just looking at it, we can see some idea. Looking at it's not going to be enough, but we can start. We can say, well, these two, they could be similar. At least the picture is the same picture. These two look like they could be similar. These two look like they could be similar. These two, same picture all the way down. There is a strong possibility that these figures represent similar objects. These ones are obviously not. This is not the same picture of the cello. These, if you look closely, are obviously not the same triangle. This one is skinnier. This one is wider. They don't have the scale. They can't have the same scale factor. And that's a cat and that's a dog. In that they both have 4 legs and a tail. In English, you could talk about the similarities between a cat and a dog. But mathematically, there is nothing similar about what's going on there. So similar figures are enlarged or reduced by the same scale. That blank is factor. This means that the dimensions of every side is proportionate. And what that means is they multiply the same. And so what we need to do is it's what we've been talking about this whole time. We need to consider corresponding sides. And so I've got 2 triangles here. We are told, well, we're not told. We're going to say that these 2 are similar. So then what are the corresponding sides here? Well, when you're labeling shapes, we name their sides based on the corners that are at either end. So this side right here, we would say that is side AB. So then side AB in this triangle is going to correspond to or be similar to what side on this little triangle? S and R. Except because we're starting at A and moving to B, I'm going to start at R and move to S. Technically speaking, S, R, and RS, while they are the same side, it's a different name. And in math, we are that neurotic about it. What is going on, front row? Jacob and Lola and your pencil got stuck in the straw. Do you need scissors? Okay. So then the next one, if I go from AB and then I go to BC, BC is going to be similar to what side in the other triangle? BC is similar to ST. And then CA is going to be similar to TR. There are sides that correspond, and everything we've done, it's all been oriented the same way. There's a couple questions we're going to look at where things are spun. When you're ready, flip the page. Okay, so here we go. We are going to start to get away from labeling which objects are the diagram and which ones are the original. You guys are going to have to start to make that deduction yourself. Sometimes it'll be denoted like this with the little arrow here. So this one, I've got a small rectangle and I've got an arrow pointing towards a bigger rectangle. What that means is we took this small one. This is our original object. And in this case, we transformed it to this diagram. The arrow tells you which way it goes. So in this case, the original object, for whatever reason, was enlarged. So if I look at this guy, this small rectangle here, we've done this a lot already. If I'm looking at the left side of the small rectangle, the corresponding side is going to be the same side, the short one, on the larger So this one's going to be 8 on the big rectangle. So then the scale factor, if you recall, is always the length in the diagram divided by the length in the original object. So this one's going to be 8 over 2, which means the scale factor here is 4. Now, if these things are going to be similar, the scale factors for the corresponding sides needs to be the same. So let's take a look at the other one. The long side in the small rectangle is 10, and the long side in the big rectangle is 40. So if these two rectangles are actually similar, what I need to get here is an equivalent scale factor. So let's check it. The diagram goes on top, the object's length goes in the bottom, and I got 40 over 10. Well, 40 over 10 is reducible. Both of those are divisible by 10. 40 divided by 10 is 4. 10 divided by 10 is 1. So I get a scale factor of 4 over 1, which is the same as the scale factor of 4. So in fact, these are similar. All corresponding parts are proportional, is what this means. Proportional. Because the scale factors are equivalent. So let's do a couple examples of checking these things. I've got 4 examples here, and the instructions for all of them are up at the top. Are the below similar figures or not? And so what we need to do, if they are not similar, we need to just demonstrate that there is a set of scale factors that doesn't work. If we claim that they are all similar, then that all the dimensions need to be checked. So let's check. In this one, which one would you dictate would be the object and which one's going to be the diagram? There's no arrows. You just kind of have to use common sense to see what we have there. What is there? We've got a box with the word fragile on it, and then a picture of a rectangle. Which one of those is probably going to be the real object? Yeah, the one on the right. This one is the one I would probably label as the object. This is the one that I would label as the diagram. You just got to be consistent as we go through it. And now we check. We want to check the scale factors for all of the corresponding sides. It doesn't matter where you start. So let's pick the long side. Scale factors are always diagram length over object length. So this one's going to be 3 over 18. This is going to reduce to, so I'm looking at this guy there and that guy there. This is going to reduce to 1 over 6. To see whether or not these things are similar, now I need to check the other dimension. That guy there and that guy there. So that scale factor is going to be the length in the diagram, so 2, divided by the length in the original object, 12. Both of those are divisible by 2. 2 divided by 2 is 1. 12 divided by 2 is 6. Oh, look, that number and that number are the same. So at least as far as this front rectangle is concerned, those shapes are in fact similar. Cool. Let's look at the next one, the one on the right. Before we do the question, what does your gut tell you? Don't forget looking at the numbers, just look at the shapes. Is that thing similar or not? Or are those two similar or not? Scarlett's gut says yes, those are in fact similar. Okay, well, let's take a look and see whether or not your gut is telling you the truth. Now, this one has an arrow drawing between the two objects. So the way that these things always are is that whichever way the arrow is pointed, that is your scaled version of the original object on the left. I know math is hilarious. So now we need to start checking corresponding scale factors. So let's look at our first set. Remember, it's always diagram length divided by object length. Let's take a look at this guy up here first. the angled side that we have a measurement for. So the diagram there is going to be 42. The object length is going to be 7. So 42 divided by 7 is 6. Okay, let's check the other one. The scale factor is diagram divided by original object. So the diagram length is 10, the original object length is 2. 10 over 2 is? Are those objects similar? No. They, in fact, Scarlett's gut lied. In the English version of similar, sure, 100%. You could make an argument that those triangles are similar to each other. Mathematically speaking, they are absolutely not. Because these two values there, those scale factors, are different. I'd like you to try these bottom two. If they are going to be similar, all of the corresponding scale factors need to be checked. As soon as you find one that's different, it means they're not similar. So try these two. On your mark, set giver. What do you find? Actually, maybe I have. It's not there. Okay. No. Okay, so lots of you are done. What did we find? For the first one, are they similar or are they not? They are not similar. Why not? You do not have to check all of them. You just have to find a pair that don't work. So the easiest way to do this is to check which set of sides. It's a shame. 56 and 14, you want to start with those two? Okay, we can start with those two. It doesn't matter which one you call the diagram or the object. Emerson asked a good question. Does it matter which one we call which? Nope, as long as you're consistent. So Emerson, which one did you do? Which one did you call the object and which one did you call the diagram? Okay, I'm gonna go the other way. I'm gonna call this the diagram and that the object. So if I do that, this one's gonna give me 14 over 56, which is 1 over 4 as it reduces. But then if I check, what was the next one that we can check to see if it, which is the one that doesn't work? The 3 and 6. We can check those. Okay, I want my diagram divided by my object, so 3 divided by 6 is a half. So these two scale factors are not the same. I don't need to check anymore. As soon as I find something that doesn't work, we're done. These ones, you have to keep going until you find something that isn't similar, so we have to check all of them. In this case, if you check all of them, you're going to find that your scale factor is what? They are similar. If you call this one the object and this one the diagram, you're going to find a scale factor of 1 over 9 for all 4 sides. If you call this one the diagram and this one the object, you're going to find a scale factor of 9 for all of those sides. It doesn't matter which way you go. The objects themselves are in fact similar. Cool. Let's use this to do some math. We've been doing math the whole time, but let's make it more interesting. Flip the page. If we know that two figures are in fact similar, then we can use scale factors and some pretty basic algebra to find unknown dimensions. Let's review fractions, shall we? If I have this, if I've got 1/3 equals x over 9, how do I find x? We want to isolate. We want to isolate x. How do I get x by, how do I isolate it? You want to do what to both sides? Right, I want to do the opposite operation. I'm currently dividing both sides by 9. So to isolate, in this case, the x, we're going to multiply both sides by 9. On the left-hand side, sorry, on the right-hand side, those are going to cancel. And on the left-hand side, how do I multiply a whole number by a fraction? You put the whole number over 1, and now we multiply numerators and multiply denominators. So this is going to become 9 over 3 equals x, and 9 divided by 3 is 3. So 3 equals x. If, for whatever reason, the unknown is in the denominator, there's 2 ways we can solve this. Let's look at the first way. We can multiply and divide to isolate the unknown. So part of what we talked about with isolating, I don't think we actually did do very many of these. If the variable is in the denominator, we want to make sure we want to get it up out of the denominator, and we want to get it alone. So to get this thing up out of the denominator, what we need to do is we need to multiply both sides by x. Isolating for something means getting it alone in the numerator. So on that side, they're going to cancel, and on the left-hand side, I'm going to get x over 3, and that's just going to equal the right side, which is 5. And now we've got the same kind of scenario that we had up here. If I want to get the variable by itself, I'm going to multiply by the denominator. On both sides, the denominator is going to cancel, and I'm going to get that x has to equal 15. That is one way that you can go about solving these. Another way is when they're both fractions, instead of using SAMDEB, reverse operations or opposite operations in reverse order, one of the techniques that you can do is you can actually flip both sides. Because they're both fractions, if you were to take the reciprocal of one side, you can take the reciprocal of the other. So I'm just going to take this fraction and flip it, and when I do that, I have to do it to the other side as well. So if I've got 7 over 2 equals 4 over x, that's the same as if 2 over 7 equaled x over 4. As long as you flip both sides. Now I've got what I want alone in the numerator, and it's just going to be one step to solve this thing. I can multiply both sides by what's in the denominator here, what I'm dividing by. And I'm going to get 4 over 1 times 2 over 7. 4 times 2 is 8. 1 times 7 is 7 in the denominator. And so we're going to get x equals 8 over 7. So it doesn't actually matter which technique you choose to use when your unknown is in the denominator. But there are ways to avoid that entirely, which I'm going to show you here in a second. So we've got an example of how we would use this. You bet. I've got these two triangles. We are told that they are similar triangles. And because they are similar triangles, by definition, what that means is they have the same scale factor everywhere. And what that's going to mean is that corresponding sides are going to be proportional to each other. And so if they don't tell you which one is the object and which one is the diagram, you can always pick it so that, if you recall, with the scale factor equation, we had the diagram length divided by the original length. If you want to avoid having an unknown in the denominator, just pick that whatever triangle has the unknown or whatever object has the unknown, that will be your diagram, and it'll end up in the numerator. So I'm going to say that this triangle, it has the unknown that we're looking for, is the scaled diagram of this triangle, the original. And because we're told that they are similar, they have to have the same scale factor everywhere. So what that means is, if I take a look at these scale factors, that the diagram length divided by the original length, 3 over 12, has to be the same as or equal to this length divided by that length. So x over 20. Because they're similar, the scale factors, and these are scale factors, have to be the same. 3 over 12 is going to be equal to x over 20. And now we can go ahead and solve this thing. To get x by itself, I'm going to, because I'm dividing by 20, I'm going to multiply 20 to both sides. There it's going to cancel. Here I'm going to put 20 over 1 and multiply numerators, multiply denominators. 20 times 3 is 60, 1 times 12 is 12, and we get that x is equal to 60 over 12. That, though, is reducible. 60 divided by 12 is 5. So then this side length here must be 5 in that smaller triangle. When you're ready, flip the page. I got 2 more examples and then I'm done. Emerson, I can't give you the reviews tomorrow either because I'm away tomorrow. So it'll be Thursday. Okay, so this one. Now I've done something to you that I haven't done yet. I've taken the objects, I've actually spun them, I've rotated them. So it's going to be a little bit trickier to figure out which ones are the corresponding sides, but that's okay, we can figure it out anyway. Because there is notation in these shapes that'll help you figure out how they're oriented. So I've got this line here, and equivalently, in the other triangle, I've got a single line on that angle there. What that means is, because these notations are the same for those two angles, it means that A and P must be corresponding corners. Because C down here has that double line, and Q over here has this double line, it must mean that these two are corresponding as well. And then, by process of elimination, B and R must be corresponding corners as well. So now we can start to actually march our way around this thing and figure out what my corresponding sides must be. I've got some unknowns here. I've got a D in this one, a variable or a side length I don't know in the small triangle. And I've got this variable over here in this large triangle, so a value I don't know here. We need to find them both. It doesn't matter what order we do them in. So somebody pick. Which one are we going to find first, C or D? Bilal wants me to find C first. Okay, cool. Let's find C first. If I want to find C first, and to make my life easier, I want to keep my unknowns in the numerator. I'm going to call this the diagram, and I'm going to call that the object. So I've got side C divided by, okay, so I've got this is the side that I'm looking for. What is the corresponding side on this smaller triangle? Well, this side here, AC, goes from the corner with the one line to the corner with the two lines. So what's the corresponding side over here? Well, it's going to be the side that goes from the corner with the one line to the corner with the two lines. So it's going to be this guy here. So this one and this one are going to be corresponding. So I'm going to have C over 4 is going to equal. It's going to equal what? Well, do I have sides where I have both values? Do I have a set of corresponding sides where I know the length of both sides? I do. Which ones? This one there, yes, 10 and 5. So I'm going to take my diagram length, divided by my object length, and now this is the thing I'm going to solve. I've got C over 4, this divided by this is going to be equivalent to this divided by this. We know this because we are told that they are similar, which means the scale factors have to be the same. So this is reducible right away. I could just say, well, this is C over 4 equals 2. So then I can multiply both sides by 4, and we're going to get that C, this length here, must be 8. Some simple algebra to solve. And now we can go the other way and we can take a look at this. We could set it up the same way. We've done it once already. Or we could see here that the scale factor here is what? How do I go from 5 to 10 and 4 to 8? What's the scale factor for these two triangles? It's 2. The scale factor here is 2. So then if I multiply, so then D, this side down here, is going to correspond to what side in the other triangle? It's going to correspond to this guy here, 6. Well, and if these two sides are twice as big as their corresponding ones over here, that means 6 must be twice as big as D. So what times 2 is 6? It's 3. So that must be then 3. We don't have to set it up the same way. We've already used our scale factor once. We could just now use proportional reasoning. And it's a relatively easy one to do. 10 is twice as big as 5, 8 is twice as big as 4, so then 6 must be twice as big as this side here, which makes it 3. When the numbers are easy, the methods are too. So likewise, I have a question like this. This question says, find the original triangle. Oh, sorry. Yeah, find the original, or no. That word shouldn't be there. The original triangle is enlarged by a scale factor of 4. They give you the scale factor. So this is the original. It was blown up to that diagram. If we know the scale factor, like we found it here, if we know the scale factor, our life is easy. If this little triangle was blown up by a factor of 4 to give you these two sides here, how do I go the other way? This triangle to this multiplies by the scale factor. In this case, it multiplies by 4. So to go the other way, what must I do? Divide each side by 4, you betcha. So then if that's all I have to do, how big is y? Well, the corresponding side is 16. To go the other way, I'm just dividing now by my scale factor. I'm undoing the expansion or the enlargement. What's 16 divided by 4? So that's got to be 4. And 8 divided by 4 is done. So now we can use our scale factors to make our life a little easier. There you go. I'm done. Here's what I want you. I know there's only 10 minutes left. I'm only going to give you a couple questions to work on. I want you guys to take a look at question 1. And I want you to take a look at question, oh, these are all the same. These are all really easy. Yeah, you know what? Just take a look at the first 3. It should be easy to do in a relatively short period of time. Once you crank those 3 out, you can be done. There's 6 minutes. Bell's supposed to go 1, and it's been going 2 minutes early all day. 6 minutes. Either way, enough time to get these things done. Yo, Mr. K.
Talking to a dean.
Yeah?
We figure it's for the 13th or 14th time. She's celebrating that.
Seriously. Okay.
Because when he had his 20th year dinner for the district, she was there.
So he's, but she's, and he started right away?
Now, he said this is the 30th.
She needs to go.